Hi, welcome to this lecture on mathematical methods for biologists. We have been discussing diffusion and applications of basic calculus in understanding diffusion. In this lecture, we will use the ideas that we learned in calculus and diffusion to study how ions diffuse. So, when in biology we know that there is so many ions, Na plus, Cl minus, K plus. So, how does this charged ions diffuse across, for example, a membrane channel? We would do a toy model to understand this. Of course, we will not be able to study the details of diffusion across a membrane channel, but we would do the simplest model to understand this. We would discuss that, and the simple mathematics that we learned so far will be useful in deriving something which is very important, which is called the Nernst equation. So, today's topic is Nernst equation, and what we will discuss is what happens when ions diffuse across a channel. This is the question that we will answer. We will answer the question what happens when ions diffuse across a channel in quotes, because we would do a toy model. So, the topic of today's lecture is Nernst equation, and we will discuss the Nernst equation. So, what we have been discussing so far is diffusion, and what we know is that if you have ion concentration difference, there will be a flow. So, now let us consider this case, the following case for ions. So, think of two separated chambers, like this is, you can think of this as two parts of a cell, like this is inside the cell, outside the cell. So, you have two closed chamber like thing, and one of this have ions. So, let us say they have KCl ions. So, you have K plus and Cl minus in water, of course. So, let us draw K plus. So, some concentration of K plus ions and some same concentration of Cl minus ions. So, I am drawing Cl minus. So, I drew plus ions small and minus ions big, because typically that is how it would be, and some other concentration of plus ions here and minus ions here. So, just to clarify at the beginning, so this is at time is equal to 0, you have a chamber in which you have these two this box separated by a small membrane like a channel, where you have a channel also, and there is a concentration of ion, like let C10 be the concentration in the first part and C20 be the concentration in the second part. So, the 0 indicates it is the initial concentration. So, this is at t equal to 0, these are initial concentrations. So, these are initial. This is important to remember, there is a final concentration, there is an equilibrium concentration which is different from this. So, C10 and C20, this could be like, for example, 10 micromolar and 5 micromolar. So, there could be two concentrations, C10 in this side, C20 in this side. Now, there is a small opening here through which only the plus ion can diffuse. So, the minus ions are too big for this opening to diffuse. So, plus ions can diffuse across this opening. So, plus ions can diffuse across the opening. So, only plus ions can diffuse. So, plus ions will diffuse. So, since there is a higher concentration on the left side compared to the higher concentration here, so we know from this that C10 is larger than C20. Of course, I have drawn more number here than here. which is to imply that C10 is larger than C20. So since C10 is larger than C20, there will be a flow from this to this. So this flow is due to diffusion. So let us call as JD. We know as of now from the discussion we had, the diffusion, the flow due to diffusion, JD, let us write it. The amount of this is, so I would write minus d del c by del x x cap. So this is the quantity. This is, if you quantify, this would be the equation for this diffusion current. What we have is this chamber with plus and minus. So you have some amount of plus ions and some amount of minus ions on both sides. Now a flow will happen of plus ions from here to here. This is a flow. So and this is what happens at t equals 0. Now after some time, let us say t is much larger than 0. So after some time, what would happen is the following. So I am going to indicate here t greater than 0. Things will diffuse. After the diffusion, some plus charge would be on this side. So you would have, let us say, different number of plus charge here and different number of plus charges here, and on the other hand minus cannot diffuse, so that would remain the same. So just remember that at t equals 0, this side was electrically neutral because there is equal number of plus ions and equal number of minus ions on the left side, equal number of plus ions and equal number of minus ions on the right side. So at t equals 0, these two sides separately were electrically neutral. After the diffusion of the plus ions from higher concentration to lower concentration, you reach this situation where you have three, in this picture you have 3 plus ions here and 2 minus ions here. In other words, since some plus ions moved from here to here, there is a net positive charge here and there is a net negative charge here because there is more negative charge and less positive charge here. Because of that, there will be a charge difference. So there will be an accumulation of negative charge here and accumulation of plus charge here. This is the situation that would be at t greater than 0. Now, if there is more minus charge here and more plus charge here, an electrostatic potential will be developed. An electrostatic potential difference. What does that mean? This minus charge will have some electric field which would try to bring back this plus ions back. So this minus charge would want the plus ion to bring back. So let me redraw this just for us to understand. So you have, so this is situation as t equals 0 I would draw, situation t greater than 0 I would draw here, and I would there were ions like this. Here I would draw the following way. So there are negative is of course much larger. So there will be a so because of this, there will be an accumulation of charges. There's more negative charges here and more than the plus charge. Therefore, this plus ions will be pulled back. So there will be a flow, there will be a force, there will be a pull, so there will be an electrostatic attraction due to this negative charges on this plus charge, and this plus charge will try to flow back. So there will be a flow Jf in this direction, there was a JD in this direction. In this case, there will be a JF, which is the current due to the force, electrostatic attraction force this way, where this plus charge will be pulled into this side, and essentially you would reach some kind of flow this way and that way, and these flows will continue. Whenever there is more plus charge here, they will flow this way back, and whenever this charge difference happens, there will be a pull back in this direction. What is the, if we quantify this JF, so let us quantify this JF. So JF is the current due to the electrostatic attraction, and which we know that C times V, where V is the velocity, and this is related to the force. Velocity is always related to force. The C F by 6 pi eta A if you have particles, spherical particles. So we ions we assume to be spherical. So if you think of this situation where you have more plus ions here, so I am drawing some different number here. This number as such does not indicate anything. This number only indicates some concentration, and there will be some other number here, and so which only indicates that there are more positive charges, more negative charges on this side and more positive charges on this side, and this positive ions will be pulled in this direction. Positive ions will be pulled in this direction, and that flow is this JF. This flow will be C times, that is the concentration at this side, times the velocity, and the velocity will depend on the force. And what does this force depend on? So now, how much would be the force due to this minus charge on this plus charge? So the force F in electrostatic, we know that force is Q times E, where E is the electric field, and this E can be written as derivative of potential. So it will be minus Q del phi by del x, which is called the gradient, and with appropriate sign and so on and so forth. So d phi by dx, the change in where phi is the potential, phi is electrostatic potential. So I use the symbol phi for electrostatic potential. If phi is the electrostatic potential, d phi by dx is proportional to electric field, and there will be an appropriate direction and so on and so forth, which can be fixed, and this formula is basically the force. So I can substitute F here, which is my Q del d phi by dx with appropriate direction, x cap or minus x cap depending on the direction you have the charge difference. So I am going to substitute this here, and so you have two, so I can substitute this for the force here. So I have two currents. One is diffusional current JD. I am going to write only the magnitude of these two currents because the direction we know is opposite. So d dc by dx. I write ordinary derivative because there is no partial derivative, because this is independent of time. I am going to discuss everything in equilibrium. So this is going to be Q C d phi by dx divided by 6 pi eta a. So I substituted wherever there was a CF, instead of F I substituted the formula that we had written earlier. So we have two currents, the diffusional current and the current due to the force, and one will flow, the diffusion of current would want things to be flowing this way, while the Jf will be in this opposite direction, and this difference, these two flows, these two currents, when they are equal, and of course they are in opposite direction, so when they are equal in opposite direction, they are equal in magnitude and opposite in direction, then the net flow will be 0. Ions will flow one way due to diffusion and the other way due to electrostatic attraction, and when these two balance, the system will reach equilibrium. So what we want? We want the magnitude of these two currents to be equal and the direction to be opposite. So the direction is opposite, which we already saw. Now we want to equate this magnitude of these two currents and see that what do we get. So if we equate these two currents, we would get an equilibrium quantity, and something will emerge by equating this. But the idea is simple, that there are two kinds of flows. When there is more number of positive ions on this side and less number of positive ions on this side, positive ions will flow from here to here. When there is more number of negative ions on this side and positive ions are more on this side, there is an electrostatic potential difference, so this plus would be pulled back and that flow is Jf. So these two flows will balance and their magnitudes are this. So we will equate these two. So let us equate these two magnitudes. So what do we want? We want d dc by dx is equal to q c d phi by dx divided by 6 pi eta a. So what we want is to equate d dc by dx with q c d phi by dx 6 pi eta a. So this is our diffusional current with the magnitude of the diffusional current, and this is the magnitude of the flow due to external force. And if you equate these two, what we get is this. Now you would rearrange this a little bit and integrate this a little bit. So I would take c to this side. So let me rewrite this. Let me take c to this side. So I would write 1 over c dc by dx is equal to, I would take everything to the other side, q divided by d 6 pi eta a, these are constants, d phi by dx. So I have derivative on both sides. I would integrate this. Now what do I mean by integrate this? Integrate this from x1 to x2. So let me just, I can put an integrate this from x1 to x2. x1 and x2 are dx. Integrate x1 x2 dx. So this integration, if I do this, here I have dc by dx dx. So this is basically dc by c. So you have the integration over c. So 1 over c dc is the what you would get here, and here you would get integral of d phi, which is phi itself. So integral of d phi by dx dx. So this is a constant. So let me rewrite this. What do we get essentially at the end of the day? So first of all, just I want to understand that x1 and x2 are this side and this. So this is x1 and this is x2. This is across the channel both sides. Now if I rewrite this, what do I get is dc by c x1 to x2. The c is a function of x1 and x2. At x1 there is a concentration at x1 and there is a concentration at x2. Is equal to q by 6 pi eta a d integral d phi x1 to x2. So if I integrate this, 1 over c integral is log c. So this is log c in the limit x1 to x2 is equal to q by 6 pi eta a d as it is, and this integral is just phi in the limit x1 to x2. So, if I apply this limits log c at x2 minus log c at x1, that is what I would get. So, if I apply this limit, what do I get? If I apply this limit, I would get basically log c at x2, which is let me call log c2, minus log c at x1, which we call log c1, is equal to q by 6 pi eta a d times phi at x2 minus phi at x2 minus phi at x1. So, this is what I would get, log c2 minus c1. This same thing I can write, as log c2 by c1 is equal to q by 6 pi eta a d delta phi, which is the change in potential. So, this equation is called the Nernst equation. Let us again rewrite this a little bit more. So, we already know. So, this is called Nernst equation, and we can rewrite this in the way we would understand it, or typically one would see this. So, I would again rewrite this a little bit differently, but this is the relation between the concentration in either sides with delta phi, which is the potential difference. So, you have two sides of the chamber. So, we have two sides of the chamber. If I call this x1 and x2, and there are ions on this. So, the potential difference across this. So, this potential difference is delta phi, and the concentration difference C1 and C2. Now, you remember the C1 and C2 are the final concentration after the current, like when the system is in equilibrium. So, just remember, it's important to remember, C1 is equilibrium concentration. This is different from C1 0, equilibrium concentration on the first side, on one side. C2 is equilibrium, that is after a long time, when both the flows balance, the concentration after the flows balance, the equilibrium concentration on the other side. And delta phi is the potential, electrostatic potential difference. So, these are the quantities of interest, delta phi, C2 and C1, and this is the relation with these quantities. So, let us write, I can write this way, that delta phi is equal to 6 pi eta a d by q times log C2 by C1. I took it to the other side, and we already know that from Einstein's relation that d is equal to kBt divided by 6 pi eta a. So, if I substitute d is equal to kBt by 6 pi eta a, I can rewrite this further as delta phi is, I am substituting diffusion coefficient d as kBt by 6 pi eta a. So, 6 pi eta a will cancel, and I will have kBt by q into log of C2 by C1. So, this is another form in which Nernst equation will be taught or familiar, where q is the charge and delta phi is the potential difference, C2 and C1 are the equilibrium concentration. So, this is called the Nernst equation. So, this is called the Nernst equation. Nernst equation. So, this is the famous Nernst equation. Now, what is the takeaway? What do we understand? Let us go back to the picture that we had before a few slides, and what we had essentially is the flow of ions on either side. So, what we have is the following: at t equal to 0, we have some concentration of ions which we call C10, C20. So, we have C10 on one side and C20 on the other side. So, here C10, C20. This is at t equal to 0, where more plus ions here than here. So, there will be a diffusion of plus ions, and since the plus ions will increase here and minus ions more here, they will be pulled back because there is more negative charge here. So, this negative charge pulls this, there will be a flow back. These two flows balance, and when they balance, you will reach a final concentration C1 and C2. So, C1 and C2 are equilibrium concentrations when these two flows balance. So, these are the equilibrium concentration. This is the equilibrium concentration. Equilibrium. At equilibrium, there will be C1 and C2 are the final concentration on either side, and the relation. So, there will be a potential difference and an equilibrium. So, this flow, this stuff will always, these flows will keep going, and this would lead to a potential difference. This would develop a potential difference. This potential difference is what the delta phi that we have. So, this is the potential difference that we will get, delta phi, because it will not be electrically neutral. There will be a potential difference, and this potential difference will be given by the final concentration C2 and C1, the equilibrium concentration, where the flows, what is the concentration at which the flows balance, that is C2 and C1, and of course the charge, temperature, and of course Kb is the Boltzmann constant. So, the final equilibrium concentration C1 and C2 will dictate the potential difference across this channel, which is the simplest problem that we can discuss, which is similar to a membrane and an ion channel. Of course, there are other activities going on in real cell which we wouldn't discuss here, we wouldn't be able to discuss here, but this is the basis using which we can build. And the bottom line is that we can use simple mathematical ideas of calculus that we learned to think about problems that is relevant in biology. So, with this, we will stop this lecture and continue later.